New pictures caught by the James Webb Space Telescope have staggered specialists. Instead of merely extending our view of the universe, these images have uncovered an upsetting reality. Our continuous cognition is deficient in grasping the possible outcomes of the universe in its beginning phases. Where the speculation of the Big Bang appears to reach its limits, this drives us to ponder new hypotheses about its origins. The inquiry arises regarding how the universe was shaped in detail and why this new discovery challenges even the most experienced analysts. To understand more about the Big Bang and the complex details of the discovery, let's examine the concept of the Big Bang itself. Contrary to standard reasoning, the Big Bang was not a blast in pre-existing space. Rather, it was space itself that began around 13.8 billion years ago, alongside matter and time. A peculiarity in material science and cosmology describes points where gravity is so intense that the arch of spacetime becomes limitless. Today, following billions of years since the start of the universe, we see that our vast home is part of a fantastic cycle. For specialists, this represents a key aspect of the universe since its very existence. It's clearly a continuous development, but it's vital to grasp that the universe isn't floating into pre-existing space. Maybe space itself is persistently extending in size. According to current hypotheses, the first stars began to shine somewhere in the range of 200 to 300 million years after the Big Bang, marking the end of the supposed Dark Ages. This was when the first luminous celestial objects coalesced to form mature systems. However, how rapidly these cosmic systems formed remains a confounding secret. An abundance of information arose through the principal pictures captured by the James Webb Space Telescope in July 2022. Specialists revealed that the telescope had identified various cosmic systems, some of which had already existed around 300 million years after the development of the universe. However, unlike the endless structures formed much later, these early universes were altogether more modest and less massive. This aligns perfectly with the scientific model accepted by specialists. The density of matter in the early universe was simply not adequate to result in worlds the size of those observed today. What began as the identification of 6 shining redshifted spots from the James Webb Telescope ended up triggering quite possibly the most critical galactic crises in recent times. Although these newly found worlds are similar in age to recently recorded worlds, they are all about as large as our own Milky Way. This has created a captivating mystery in Big Examination. Following the analysis of a series of pictures caught by the near-infrared camera, specialists identified the aforementioned light sources utilizing redshift to confirm that the light from these objects took more than 1 billion years to reach our eyes on Earth. Thus, we are dealing with structures that had previously existed around 570 million years after the assumed Big Bang. By dissecting the attributes of these designs, it was concluded that the Webb telescope had captured 6 early worlds in the pictures. Surprisingly, these universes were so enormous that they challenged normal suppositions in cosmology. Rather than finding the average smaller universes, structures were identified that were almost as extensive as our own Milky Way, regardless of having formed early in the universe's history. Assuming we proceed to examine the data accumulated by the James Webb Telescope, this gravitationally bound bunch of stars was already more than 10 billion times the mass of the Sun at that time, with one possibly outperforming the 10 billion solar mass mark. However, whether this scenario is accepted, the mystery remains unsettled. Indeed, even for this case, there would be significantly more luminous mass in the early universe than previously anticipated, presenting a problem. The identified objects contradict practically all conventional cosmological hypotheses. If only one of these cosmic systems ends up being real, it would challenge our earlier assumptions. Moreover, the density of matter in the early universe would have to be a few times more prominent than previously expected to account for this peculiarity. Another likewise bizarre explanation relies on how these cosmic systems formed in a way that remains completely dark to us. These revelations and the conversations surrounding the Big Bang have prompted numerous scientists to drift away from this hypothesis. Various astrophysicists with alternative perspectives feel their points of view are not being heard in scientific journals. Even those who express doubts about existing theories are often labeled as ridiculous. Yet, it is clear that even specialists who still advocate for the theory of how things came to be are continuously faced with questions without conclusive responses. These requests include specific issues like why and how, 13.8 billion years ago, something literally arose from nothing. Could something truly start from nothing? Or was there some triggering event? Or was it all just an accident? Steven Weinberg pointed out that the concept of time as we understand it began exclusively with the Big Bang. Thus, this process could not have been set off by something outside it. A similar contentious question relates to the consistency of radiation and density throughout the universe. Regardless of which direction or at what distance we look on a larger cosmic scale, we find similar densities and distributions of galaxies, nebulae, and radiation everywhere. Regular examiners explain this peculiarity through the theory of cosmic evolution. However, different specialists take this assumption further with a theory of tumultuous evolution. According to this thought, evolution has only stopped in specific regions, like bubbles, and continues endlessly elsewhere. This suggests that various universes could be forming in these bubbles, each with its own unique physical regulations. Within this model, a critical inquiry emerges. What if the universe doesn't represent the whole? More intriguingly, consider the possibility that another universe existed before our own. In this case, the Big Bang would become part of a larger cycle. According to this perspective, our universe is part of a more prominent, diverse design. Within this structure, the chance of an immortal pattern of breakdown and restoration of the universe is advanced. However, this is not the only perspective presented in the realm of cosmology. Besides the hypothesis of the universe's beginnings, in 1955, for example, an article appeared in NASA Space Times contending that there could have never been a Big Bang since the universe has existed for an infinite time. In this view, the expansion of the universe would be non-existent, and the consistent arrangement of matter could give the impression of a steady evolution. Additionally, another intriguing theory arises from the realm of quantum physics and string theory. Some tests have proposed that our universe and all that is in it might simply be a flat three-dimensional image projected onto a surface. Hence, there is a plausible idea that our reality is a result of a higher simulation. While this could seem like the plot of an unconventional sci-fi film, it might indeed be connected to the Kardashev scale, which gauges the level of progression of a civilization based on its capacity to harness energy. If there were a Type 3 civilization capable of fully harnessing the power of an entire universe, it might have created a perfect simulation. Investigating the depths of cosmology and the beginnings of our universe leads us into a domain of significant mystery and ongoing scientific inquiry. The new pictures caught by the James Webb Space Telescope have reignited conversations about the actual texture of our world, testing laid-out speculations and inciting researchers to reevaluate essential parts of cosmological understanding. At the core of this inquiry lies the hypothesis of how things came to be, an underpinning of current cosmology. As indicated by this hypothesis, around 13.8 billion years ago, the universe arose out of a phenomenally thick and hot state, growing quickly and resulting in spacetime and matter as we grasp it today. This cosmic event is not just a blast inside prior space. Rather, it might involve the very beginning of space itself. The concept of a peculiarity, where gravitational forces are so extreme that spacetime becomes boundless, supports our understanding of this early-stage epoch. However, the discovery of early systems by the James Webb Telescope challenges our assumptions about how rapidly structures formed in the universe's earliest stages. These systems identified within a few hundred million years of the Big Bang appear astoundingly developed and massive in opposition to assumptions based on current cosmological models. One of the big inquiries raised by these findings is the concept of vast expansion. As indicated by the prevailing theory, expansion happened within parts of a second after the Big Bang, causing the universe to develop dramatically. This rapid development would make sense of the consistency of the cosmic microwave background radiation observed across the universe today. However, the new disclosures propose intricacies in the early universe's development that may require changes to inflationary models. The development of universes like those seen by the Webb telescope prompts cosmologists to reconsider the circumstances and cycles governing the universe's initial development. These cosmic systems, now critical in size and mass, suggest a density of matter that surpasses past estimates. The mystery extends while considering how such enormous designs could shape and develop in a relatively short cosmic timeframe. Besides, the discovery of these early systems raises interesting inquiries about the nature of dark matter and dark energy, two elusive components that comprise the majority of the universe's mass and energy content. While dark matter is accepted to provide the gravitational platform fundamental for galaxy formation, the distribution and properties of dark matter in the early universe remain uncertain. In accordance with these astrophysical mysteries, theoretical physicists are investigating alternative cosmological models that challenge the regular Big Bang perspective. Some hypotheses suggest that our universe is simply one among many in a vast multiverse, each with its own unique physical regulations and constants. These thoughts, emerging from advancements in string theory and quantum cosmology, propose a more complicated and interconnected universe than previously envisioned. One thought building up forward movement is everlasting expansion, wherein universes constantly arise from a larger expanding space. This speculation posits that our universe could be just one bubble among countless others, each with its own specific properties. The challenge lies in finding observational evidence to support such hypothetical ideas as they push the limits of experimental confirmation. Another provocative theory is that our universe exists within a simulated reality akin to a computer-generated game. This thought draws parallels to advancements in artificial intelligence and computational science, where simulations can replicate complex systems with surprising accuracy. If true, our perception of reality as a solitary physical universe could be fundamentally altered, raising critical philosophical and scientific inquiries about the nature of existence. Moreover, advancements in observational cosmology continue to reveal the universe's boundlessness and complexity. Telescopes like the James Webb Space Telescope, with their remarkable sensitivity and resolution, promise to uncover significantly more secrets of the universe. Future observations may shed light on the earliest moments of the universe, providing insights into its ultimate destiny and the fundamental principles that govern its development. Beyond observational cosmology, particle physicists are exploring the fundamental particles and forces that shape the universe. The mission to unify gravity with the other three fundamental forces, electromagnetism, strong nuclear force, and weak nuclear force, remains a central objective of theoretical physics. Ideas like quantum gravity and string theory offer potential frameworks for understanding these major connections at both the smallest and largest scales of the universe. In the domain of quantum mechanics, the concept of time itself remains a subject of intense discussion. Time, as a direct movement from past to future, is challenged by quantum theories suggesting that time might be evolving or even elusive at a fundamental level. Understanding the concept of time within the context of cosmological models could reshape our perception of the universe's origins and development. Moreover, the quest for extraterrestrial life continues to captivate public imagination and drive scientific inquiry. The discovery of exoplanets, planets orbiting stars beyond our solar system, has expanded our understanding of planetary variety and the potential for habitable conditions elsewhere in the universe. Future missions, such as the James Webb Space Telescope's investigation of exoplanet atmospheres, may provide evidence of biosignatures indicative of life beyond Earth. Notwithstanding these scientific endeavors, social and philosophical reflections on the universe enhance our understanding of our place within it. Inquiries concerning the meaning of existence, the possibility of intelligent life elsewhere, and humanity's future in space exploration provoke thought and conversation across disciplines. As we stand on the brink of a new era in astronomy and cosmology, energized by technological advancements and theoretical breakthroughs, we are reminded of the significant interconnectedness of everything, from the smallest subatomic particles to the vast cosmic structures spanning billions of light years. Overall, the investigation of the universe and the origins of existence is a journey that transcends disciplinary boundaries and challenges our most fundamental assumptions about reality. The discoveries made by instruments like the James Webb Space Telescope offer tantalizing glimpses into the early universe and insight into new inquiries regarding evolution and development. As we continue to unravel the mysteries of dark matter, dark energy, and cosmic expansion, we move closer to a broader understanding of the universe and our place within it. Through collaboration among cosmologists, physicists, philosophers, and technologists, we embark on a grand journey to decipher the universe, a mission that promises to redefine our understanding of existence itself. Whether exploring the depths of black holes, grappling with the trajectories of distant galaxies, or examining the nature of reality, Each discovery brings us closer to unraveling the complex tapestry of the universe. As we venture further into the cosmos, guided by curiosity and driven by a desire to grasp the universe's vastness and intricacy, we are reminded of Carl Sagan's words, "Somewhere, something incredible is waiting to be known." This sentiment encapsulates the essence of scientific exploration, a continuous journey of revelation, wonder, and enlightenment that continues to inspire generations of scientists and thinkers alike. In the words of Albert Einstein, the most beautiful thing we can experience is the mysterious. It is the source of all true art and science. As we confront the mysteries of the universe, we are invited to embrace uncertainty, challenge our assumptions, and seek new perspectives that expand our understanding of the universe and ourselves. In this way, the exploration of the universe is not only a scientific endeavor but a profound human mission for knowledge and meaning, an odyssey that transcends the boundaries of space and time, inviting us to contemplate our place in the grand tapestry of existence.